Alrighty, this video is going to be kind of an origin story for this whole series. If you try and explain this stuff to people, they look at you like you're crazy, and then they say, "How did you know that?" And the answer is, I already knew it. I just did, just chance favors the prepared mind, I guess is the phrase. I was just prepared to know it, but that seems to be the story of my life. Um, so my undergraduate degree, I got a Bachelor of Science degree in geology, and people ask me, well, why did you do that, or how did you make that decision? And the answer is simple. Uh, I mean, I was just a really bad student. I've been a bad student all my life. I was more or less forced to go to college, and then I was more or less forced to pick a major, and I picked geology for the same reason that a dog licks his balls, because I can. And it really didn't. It didn't. There wasn't a lot of thought to it. There's not a lot of thought to anything I do. Anyway, probably the biggest reason that I did it was because I had an older brother. He was already in that school, and he'd already picked that major. I thought, wouldn't it be great if I had somebody who would shepherd me around and teach me how to do stuff? And then, as luck would have it, day one in geology, prettiest girl in the class who wanted to be a geologist and became a geologist, became my wife. So I got my brother and my wife and me, and so we all share the same common experience, but we clearly didn't experience it the same way, and that's not unusual because I don't experience things the same way other people do. I go through life very confused. I'm so simple-minded, I can't figure out what people are talking about. So I just pretend like I know. I pretend like I understand what they're saying. So, if you want to understand geology, then you got to understand the earth. That's what geology is. So what's the earth? Well, you got to understand time. I mean, time is a big part of geology, and of course space is a big part of geology. So you start at time zero and there's no earth, and then you wait and wait and wait, and in the meantime the universe is generating these things called atoms, which is the only thing you really care about. And then after about 10 billion years, boom, there's the earth. There it is. It's a big ball of atoms. So that's step one. Step two is to figure out, how do you put these atoms where they're supposed to go? How did the earth put them? They're in perpetual motion. We just assume more or less it's the same ball of atoms. They're the same atoms, but they keep moving around. They keep rearranging themselves. So you've got different kinds of atoms. You've got different layers of atoms. You get the middle of the earth. You get the crust. We're mostly concerned about the crust, but then they move and they crash into each other and they make these shapes. Um, so all you got to do to be a geologist is figure out what the hell these atoms are doing. What is it? What are the rules that make these atoms do what they're doing? Let's try and get these rules down to a few. Let's not make this more difficult than it needs to be. Um, Geology is not that hard, but they try to make it too complicated. One of the things they do is, okay, so a rock is a mineral. We're describing rocks. So they define a mineral, and they explicitly exclude life from the definition. Well, what in the hell are you doing? I mean, you can't go anywhere on Earth and not see life. And you can see that it's actively arranging these atoms. How do you exclude it? And they don't give you a good reason. I mean, life meets the definition of a mineral. And I'd go one further. I'd say it meets the definition of a crystal. So we need to start thinking about life as a crystal. And that's what most people are always saying. Jesus. Never mind. Anyway, so I'm not going to do that. I'm going to say life's a mineral and it's a crystal. And if we're going to understand it, we got to understand it in those terms. So, you take a rock. This one's called halite. We know it is salt. We know that it's sodium and chloride. And then we can imagine how these atoms position themselves, and then we can know that the positions of these atoms lead to the properties of the rock. And we can test these properties. We can look at them, we can pound them with a hammer, we can lick them with our tongue, and we can scratch them with a nail. But the basic idea is that the properties of the atoms and the positions of the atoms are going to dictate the properties of the solid. So that's the goal. Well, I think if that applies to minerals and we're a mineral, then it should apply to us in life, and we can do that. So one of the first days, you go into geology, they're going to explain to you how this works. They start showing you wallpaper because you're going to use this wallpaper to figure out how these atoms behave. Well, before I went to school and tried to become an adult, I was a graphic artist. So I'm familiar with wallpaper. It's just graph paper. So, and that's all minerals are, according to them. It's just graph paper. So as you spend more and more time learning this stuff, you start to realize that there's something wrong with what they're telling you. There's a lot of things wrong with what they're telling you. That's true of all science. And so when you go through this graph paper routine, you realize that it's logically impossible for what they're describing to be real. So we're just imagining, we're pretending like it's real. And then we're going to create all this language to confuse each other. And the more confused we get, the more we believe that it is real. So in the case of crystals, what they do is this French guy named Bravais, who was a mathematician, he didn't know anything about atoms. This is the late 1800s. He comes up with this system of graph paper, and they name him after him. It's called the Bravais lattices. And all it is he says these are the only ways that atoms can be arranged in space and be crystals. Well, we know this is false on many different levels, but we don't want to say that out loud. So he says, okay, here's your 14 pieces of graph paper. And so it's not just graph paper. What we normally think of as graph paper, is a square grid. Well, this is just one kind of graph paper. It's called a Cartesian graph paper. And we're going to go into the difference between Cartesian and non-Cartesian, stuff like that later. But that's what it is. And what it is a mathematical graph. So we just have nodes and edges, and then we have to project these things into space, and then we have to project those things out into space again. Well, there's a lot of assumptions in this process that are false. It's nothing but a ginormous homunculus. What it is the difference between cause and effect. It's that we can understand this, and so we look at nature and we say, this is what causes it. But the atoms consistently reply to us, no, they don't. They don't do that. So you take things like a snowflake. Well, that's clearly a mineral. It's an ice crystal. Well, you're not going to find a piece of graph paper that defines a snowflake. And then you take these other things that were only being discovered at the time they were teaching us this. They're called quasicrystals. Well, we know for a fact that we're not going to find a piece of graph paper that's going to describe a quasicrystal. It's mathematically impossible. And then you take a life and you say, well, if it's a crystal, then show me the graph paper that's going to describe that. So I got it in my mind that let's just assume that there is such a piece of graph paper. And I would call it a universal graph paper. So in other words, instead of giving me these hokey 14 pieces of graph paper that are all premised on this idea that there's 3 dimensions in space, which is false. It's obviously demonstrably false. And that we're going to then create information, a unit cell, and we're going to project it out. So If we do salt, then all we got to do is project the unit cell out. Boom, boom, boom. This is the unit cell. And then all we're doing is projecting it on 3 axes. That's all you do with crystals. But then you create all these elaborate languages and notations so that you can impress your audience and then confuse everybody. And then at the end of the day, they say, well, oh, geez, that's fabulous. Well, no, it's bullshit. It doesn't work, because the times where it does work are the extreme exceptions. Okay. And the times where it doesn't work is almost all the time. I mean, if you go out and find rocks out in the wild, they don't conform to this idea. So I got it in my mind that, instead of having all these pieces of graph paper, these different special graph papers, special. Now let's get one piece of graph paper. Let's have one idea that we can reduce and then project it out into all things. So then instead of having the crystals be the general case, the non-crystals are the general case, and the crystals are the special case. And this is true of math in general. I mean, these crystals these normal crystals, they're perfectly Euclidean. Well, the universe is non-Euclidean. It reduces to Euclidean crystals. So that the quasi-crystal is the general case. If you can understand the quasi-crystal, then the other normal crystals would be, well, these quasi-crystals are so bizarre because they're based on, Penrose tiles, and there is no unit cell. That's the problem. Well, okay, it's just like Einstein. You say, well, if this must be the truth, this must be the invariant, then that must be what we must build from. So if there are crystals that can have no unit cell, then that must be the general rule. And then the special rules are the ones where they do have unit cells. So let's just flip this cause and effect on its head. Well, now you've got a problem because now you've taken something that's seemingly simple, which is actually not simple, it's complicated. And you've made it hard, but actually we've not made it hard, we've made it simple, because we're gonna take just a few rules and then we're gonna project them out into space, and then we're gonna derive the rest of it. So the idea is universal graph paper, and I actually I can't actually make universal graph paper. I don't know if anybody can. Oh, let me put it to you this way. I know one thing that can make universal graph paper: life. That's what life is doing. Okay, it's plotting out atoms. It's telling atoms where to go with very high precision, a very high amount of efficiency. I mean, the probabilities are just outrageous the way it's doing it. What it's doing is making a plot. It's making an atomic plot of the most complex graph paper. It's the most complex crystal. That's why it's aperiodic. And so in order to do this, what it has to do is it has to reduce entropy at the lowest levels so that it can expand entropy. It's creating the smallest sets so that it can generate larger sets of information. So it's doing exactly what Erwin Schrödinger said. It's an aperiodic crystal. It's aperiodic because A, there's no unit cell, or at least there's not a unit cell that we can easily identify. And B, the structure is so large and complex that in order to build it, it takes more atoms than the number of atoms in the universe. So it can't be repeated, from a pragmatic standpoint, because the structure is too large. So that actually works. At least in my mind, it works. So I would say that life is, I don't know that I'd say that it's a quasi-crystal. A quasi-crystal, although it's more complex than a normal crystal, I don't think it's quite complex enough to describe life. So I would rank it regular crystal, quasi-crystal, life. And I would say the difference between life and a quasi-crystal is that a quasi-crystal is a solid, and life is something that is not a solid. It's more of a liquid. It's trying to learn how to be a solid. It's trying to learn how to be a perfect solid. So it's a it's about entropy. So I think we get entropy a little bit confused. Let me see. So this is the equation for the ideal gas law. And so an ideal gas is the idea that these atoms are in motion, and these symbols represent pressure, volume equals the number of atoms times a constant times temperature. I think that's what that means. But in my mind, what it means is it's about entropy. So the gas has this amount of entropy, but there's two different kinds of entropy in this regard. There's the entropy that is thermodynamic, which Boltzmann described. It's statistical entropy. And then there's the entropy that's positional, which is what Shannon described. So what we need to do is we need to see life as the both sides of that coin. So while these atoms are moving, they have a lot of you have to not just account for their positions, but they're changing positions. So the amount of information to describe it is very large, but at the same time it's random, so it's very small. All you need to do is describe randomness. But then as they slow down, they seek less random configuration. What the atoms are trying to do is reduce the entropy to the maximum extent possible given the circumstances. So for instance, quartz, when it cools very fast, it doesn't have the opportunity to sort through all the spatial arrangements, so it creates obsidian, SiO2. It's a glass, and it creates these spherical fractures. So the circumstances won't allow it to find a more organized state. So a smaller configuration, less information. So if they're allowed to find that state, then they'll do quartz, which is a crystal, a prismatic, has planar surfaces. So this is what atoms are trying to do. So we can imagine that this is the ideal gas law, and as the animation decreases, we have an ideal liquid law, and then we have a law of ideal solids. So it's a continuum of entropy. We can imagine. Nobody's ever said ideal solid law, but clearly there is one. We just need to state it. So these atoms are seeking this ideal solid, but in life they get blocked at the liquid state, because the one thing that the atoms have to do in life is keep moving. If they don't keep moving, then they die. So it's an animation. So it's more of we are liquids. We're not. It's not about cooling. It's about precipitation. We're precipitating out of seawater. So we are seawater. It's just that since we're animated, we can climb out of the sea and move around. So we're animated crystals. We're animated ideal solids, or at least the goal of life is to create these ideal solids. So in my mind, these geologists are making this too complicated. We could simplify it. We can reduce it to like one set of graph paper that encompasses everything, a universal graph paper. And we can reduce it to one rule for all the atoms. And now we can start looking out over the earth and recognize that life is creating geologic formations. Most of the crust is formed by this force of nature called life. We can explain it logically with the same tools that we explain the atoms that we don't consider to be life, and then we don't have to draw a line, some magical line between what these crystals are doing and what life's doing. The only thing that life is doing that salt's not doing is it's trying to learn. It's a learning crystal. It's an animation of spatial information. So now all of a sudden, what we're trying to do is we're trying to find a unit cell for life. Well, as luck would have it, this is it. So now we can see the similarities here, but we can also see the differences. But the main difference is we need to animate the unit cell because it's a language of animated symmetry. So I actually invented this machine because I thought it was a machine that would generate universal graph paper. I didn't just think it would, I knew it would. That's why I built it. That's why I was building it. And so I already had it, and I looked at the codon table, and I said, oh my God, I can map this onto this, and now I've generated a mathematical graph that's consistent with what I'm trying to do, which is create a language of positioning atoms in space. So it only took me, I'll demonstrate, with these perfect solids how I did this. It only took me a few minutes to do that because it seems obvious. And then it only took me an instant to realize what it was. It was an emulation of the language of life. Well, once you know that, then you know a lot. You know a little, you know a lot. And then you can start, thinking about it, and you can start saying things that are true about it. And then you can actually start making sense out of what life's really doing instead of just this ad hoc, superstitious, idiotic story about what life's doing. So I don't know why people get so mad when you tell them this. It's not that hard. Okay. There's no reason to get mad. There's no reason to yell at me. There's no reason to gaslight me. Okay. This is, quote, simple math. But we're going to have to get into the simple math, which is where people lose the thread. They lose the narrative because they believe that math is real. I don't. I think math is 100% artificial. It's contrived. It has to be. It always is. So if it's got to be contrived, let's contrive one that actually works for what we want to do it. Which, once again, I must repeat, we got to put on our big boy pants and get busy.